Welcome to the fifth lab of this course. Today we'll be using our first IC, the operational amplifier, also called the op-amp. The op-amp is the foundation of almost every electronic devices we use today. In fact, you may implement a speaker later in this course. Before we start the lab, let's take a look at the op-amp first. This is the appearance of op-amp with dual inline package. The notch here is to identify the top of the IC. When placing the notch at the top, pin 1 is on the top left corner. Pin 1 can also be identified by the dot here. The position of the other pins are shown in the figure. Let me show you an actual picture of an IC. There you go. You see the notch here and the dot here. That makes this pin 1, pin 2, and so on. The op-amp has to operate with minus 15 voltage and 15 voltage. Connect both pins to the correct value. Be careful that if you connect it in the wrong way, the op-amp may break. The two inputs are connected to pin 2 and pin 3, while its output will be in pin 6. Here is part of the data sheet of our op-amp. It lists several important electrical characteristics of our IC. The data are tested under these conditions, including the driving voltage, temperature, and other specific testing conditions listed here. The result also varies. Therefore, it lists the range of the characteristics. Usually, we'll look for the typical value. Data sheets are important because it provides a realistic data of the device, instead of the ideal model of op-amp that we've learned. It shows you the limitation of the device and helps you to determine whether to use the IC or not. For example, we often idealize the input resistance to be infinity. But according to the data sheet, you know that the Rn is typically 1 megaohm. The value will affect the approximation of the ideal model under certain circuit configuration. To provide the positive 15 voltage and minus 15 voltage, we'll use the power supply. Recall from the first lab of this course, we have to connect the master and slave as the figure shown. Because our op-amp is very delicate, we'll need to limit the current, otherwise the op-amp will burn. Limit the current to 0.02 ampere to avoid tragedy. Experiment 1. We'll explore several basic characteristics of the non-inverting and inverting amp. Step 1. Construct the circuit A and short VI to ground. Record Vout. You'll find the output Vout is not 0. Explain why. Step 2. Input a sine wave with the following configurations from V input from VI. Record the VI, Vout, and calculate its gain. In this step, you may utilize the average function on the oscilloscope to get better results. Step 3. Measure the impedance by the multimeter, but you may skip this step. Step 4. Calculate theoretical gain of the circuit B. Step 5. Input the sine wave with the following configuration from VI to the circuit B, and record the waveform of VI, Vout, and calculate the gain. Step 6. Input different waveform and different frequency, and record the input and output waveform, and calculate the gain. Step 7. Measure the input resistance using the concept of voltage. We know when constructed a circuit as this, when the voltage of this point is half of the input voltage, then the resistance of Rx equals to the input resistance. Therefore, we may use a variable resistor of 10 kilo ohm and adjust it to make this point to be half of the input voltage. Then we'll compare the difference between two amplifiers. Finally, design an amplifier with the following circuit configuration such that the gain is -100. Record the waveform of VI and Vout and calculate the actual gain. You may design it using the following formula. The design need not to be precisely -100. Just try to approximate it as good as you can. Experiment 2. Complete the two different voltage follower circuit and compare them. Note that the amplitude shown here with the subtext of PP means that the peak-to-peak voltage is 10 volt. Set the input signal so that its peak-to-peak voltage be 10 volt. Experiment 3. Complete the weighted adder circuit and input it with two different square waves. Record the waveform of two inputs and the output. The difficulty of this lab is to provide two different square waves. There are two different ways to do it. The first one is to use the Regal function generator and provide two signals. For the details of the operations, please refer to the other video we filmed specifically on this topic. Because not all people has the Regal function generator, here we show another method that will provide two different signals with one signal source. Using the concept of Thevenin equivalent circuit, we can transform the circuit on the left, specifically the V2 and R2, to become the one in the right. While measuring the peak-to-peak voltage of the square wave, use the cursor function. If you use the peak-to-peak function supplied by the oscilloscope, it is very likely that the value is corrupted by the phenomenon called overshoot. So use the cursor function to measure the peak-to-peak voltage. Experiment 4. Complete the circuit and input the following signal using the method that we described in the previous previous experiment. In this lab, in order to show the effect of the difference amplifier, we wish you to record clearly the relative positions of V1, V2, and Vout. You may record twice V1, VO, and V2, VO, and put it on the report, or use two oscilloscopes and set them to the same trigger level on Vout. Remember to use the cursor function to measure the peak-to-peak voltage. Then, the bonus lab. Remember that we talked about using the voltage divide technique to build two signals from one source. A common starting point is like this. However, you know that this is not the same as a circuit in experiment 2, because the voltage dividing circuit also has an output impedance. Therefore, we have to use the concept of Thevenin equivalent circuit and calculate the correct resistance value. However, if we utilize the op-amp and connect it to form a buffer, then we need only consider the voltage dividing circuit. The buffer has the characteristic of large input impedance and provides almost zero output impedance. Therefore, it can transfer the voltage almost ideally from this point to here and become the second signal provider that we needed. That's all for this lab. Have fun.